to summarize how you're going to do the sampling. If you have a big data, big, as big as you want, you have no problem. Just code out 1/3 and then the 2/3 to do the training. Or even 1/3 for training, 1/3 for testing, 1/3 for touring. That's all fine if you have like the weather data. But unfortunately, you don't have that. What you do, the most frequently used is bootstrap or cross-validation. Sometimes you do the leave one out, or depends on how small your size is. If it's very small, I would say you do the leave one out, cross-validation, or you do the bootstrap. That's how you can make it good. But that's practical for your project. And the next question is, how do you compare? Whose is better? That's the hard part. And you need to really use the statistic to convince people you say mine is better than yours. Well, if you just did the practice, okay, you just do all the 10 for the crossover validation, and after all the tests, you find the one approach have a small error, then you claim you get this is the best. Okay, that could be pass a GRP project, but it cannot pass a PhD thesis. This could be go to a conference, but I want to publish in a journal paper, because you did not convince people. This is just empirical study. Empirical study just to say maybe you're right, but they cannot say you prove you're right. Those people doing their PhD in computer science, they really need to consistently prove why theirs is better, not just empirical. That's another issue. Well, of course, an approach, if you can, is called a paired t-test. Means put the apple and the orange side by side, compare everything. That's what you do, and that's start from William Gossett, and why is it called the student test? Because he made this great contribution in statistics, but he only signed his name as a student. And then this one later on be famous student test or t-test. Very, very frequently used. What you do is distribution of the means. That procedure, I think it's statistics. If you don't learn statistics, that wouldn't make any sense to you. Basically, this is one population. That's another population. And you make this 2K samples. In each of them, you find the mean of that population and the mean of this population. And there, because you did a K further, then your standard deviation reduced by K, right? And then you're going to compare this, that's the Z value, with this, with the shift and the compression. And then, if this K is big enough, this sample size is big enough, they should follow the normal distribution. Follow the normal distribution means if they are really different enough, they're going to be in the outside of that confidence error. Then you can deny the null assumption. That's put side by side. But it's hard. Most of the time, you probably won't get out result, because you need this difference. Depends on how much confidence. If you want 1% of the confidence, you only have 10 of sample size, you really need that much difference. That means you need to have 3 difference at least. Then you can claim probably they're different. That means their mean, 1 you throw 10 times, 1 you always keep get 8, another one below 5. Then you can claim something. Otherwise, you can't. If your sample size is bigger, they say 100, but a lot of practice actually over 30, you can start to use the normal distribution. And now your difference is about 2.3, and then you can claim 1. That's 98% of confidence. because it's two sides, that's one side. And this is 90% of confidence, you have 1.65. We looked at that before. Okay, you look at that difference, look at this to see what's the distribution. If it's in the other side, you can claim, you can deny, you say it's unlike they are the same. If it's the other side of the, let's say 1.65, if you want the 90% of confidence area, then you want the 1.65 difference, then you can claim out. Right by that, and then instead, use this to look at the t distribution. It means when your sample size is not too big. Use that. Again, those you calculate, you look at the number and look at the table, you're going to make a conclusion. And I'm sure if you are integrated level, senior level, you can always find the number and make the conclusion. What I'm saying is, I understand what does that mean. that's the thing. Really, you need to take some time to figure it out. Okay, now the next thing I want to talk about is predict the probability. And we just talked how do you compare, say one is better than the other. But now I want to ask you, how do you say how much confidence you have? What's the possibility you can predict it right? So there's a few measurements, but none of them are ideal, are very good, or are winning. One thing of just 0 or 1 loss function, you just count how many times out of n you just missed it, or how many times you hit it, and hit and miss, that's easy. But this turned out not necessarily good. It really depends on, first of all, good and bad. Let me just back up to what I talked before, how to compare. Compare which algorithm is better is really domain related. Really depends on what you're talking about. There's not a single thing says best in everything. There's just something best on some different data set. In here, most of the time, it really depends on the application. It really is more reliable for the probability estimate. There's a lot of things have the probability estimate. For example, Bayesian always give you the probability. If you win by how much chance? Odd, right? You remember in the end, belongs to which class? It's just the probability. Sometimes it could be win by 1%. That's a marginal win. Sometimes win by 60%. That's a huge win. That's comes with the probability of the confidence. Or the decision tree. When you classify everything to the root, to the leaves, to the final result, you might, if the data is big enough, have 100 instances. Among the 100 instances you classify as A, only 80% is A, 20% could be B. If that's your case, your probability is clear. You only have 80% of accuracy. Just get to this case. So when you have this, it's better. So here's an approach called the quadratic loss. So why we always want to square? Well, when you deal with the error, you always want to square it because the error could cancel out each other. Sometimes you got positive error, sometimes you get a negative error. If you don't square it, they're going to cancel out. You say, two mistakes make it right. That's not going to happen. So simple as this. If you have k different classes, and your character actual class is C, ideally, you remember the confusion matrix. If let's say just k equal 2, ideally you only have 0 and 1. If it's the right class, you have 100%. If it's the wrong class, you have 0%. This is the ideal case. But if you come with the confusion matrix, you remember the precision and recall, and this you have 2 positive and 2 negative, false positive, false negative, then you got a different probability. So the probability you get from your classified which is the ideal probability, you just square it. That's the quadratic loss function. Simple like this. And you might say, oh, I had a very bad classifier. Every time I end up 50%. And then 50% ideal is 1, you're going to maximize this error, right? It's 1, 0, you have a 50-50, and you add this one, you can get the maximum error. That's just bad. If you have 2 classes, you get a 50% of error. Don't need to do anything, you can get that. Just random, right? Another way is use the information loss function. Oh, I pretty much, too much, forget it. Anyway, let me finish. The true class probability, that again is a sample. How do you know the true probability? Unless your sample data is infinity, you don't have the true. But this is the probability you get from each class. 1, K1, Pk, that's the probability of your classifier. That's the true probability if you really have many training sets and many testing sets. And then, of course, that information loss function, again, that's the entropy. It's going to be minimized when Pj equal this, when yours converge to the reality. That, again, depends on how much training, how much coverage, how much everything. So the bottom line, why you have probability in the first place? Well, you can do perfect job. But if the learning example is bad, they have a self-contradiction. I have exact the same attribute, but one class for A, another class for B. What you can do? You cannot beat any of those, right? So you always have a probability because you are dealing with real data. Real data never is like a mathematical right. You only have the right answer or wrong answer. They just give you the wrong training case. You cannot beat that. Are you with me? So you always have probability. But the information loss is the best you can do is you just get the reality. Because you are doing the sampling, but you want to reflect the whole population, it really depends on how much you sample. If I really get the number infinity, let's say I have billions of population, I each time do 1,000. I do hundreds of times, then I have hundreds of thousands of them. You bet, that's pretty close. But that's, again, it's a computational cost. Everything now you count as a cost. And this now it costs you time. Well, for medical data, cost time maybe is okay.